ancient skywatchers, the Milky Way was a mystery that became a myth. The vastly expanded Milky Way was only a small piece of a far grander cosmic reality.
In the quiet outer reaches of the Milky Way, a thin river of ancient stars drifts through darkness, following a path shaped billions of years ago. Yet somewhere along that path, something unseen struck, bending gravity itself and leaving behind a wound that astronomers are only beginning to understand. The quiet river of stars. From Earth, the Milky Way appears calm, a pale band stretching across the night sky, but beneath that stillness, the galaxy is constantly moving, reshaping itself through gravity and time. Stars do not simply orbit in neat circles. They travel in vast currents, some of them the remnants of smaller galaxies torn apart long ago. These stellar streams form when gravity pulls clusters apart, stretching their stars into long, delicate ribbons that preserve the memory of ancient collisions. Astronomers study these streams because they behave like cosmic tape recorders, quietly storing the history of everything that has passed through them. One of the most remarkable of these structures is GD1, a narrow stream of stars discovered in the early 21st century, stretching thousands of light years across the galaxy's halo. Unlike the dense spiral arms filled with gas and bright young stars, GD1 is thin and fragile, made mostly of older stars moving together along a shared orbit. Its simplicity makes it unusually valuable because even a small gravitational disturbance can leave a visible mark in its shape. In many ways, GD1 is less like a river and more like a strand of silk suspended in space, sensitive to the faintest touch. For years, astronomers assumed GD1 was simply another relic of the Milky Way's violent past, quietly orbiting in predictable silence. Then high-precision observations began revealing irregularities that should not have been there, subtle distortions that hinted at an encounter powerful enough to bend the stream without leaving any visible trace behind. What looked at first like minor noise in the data slowly transformed into a puzzle, suggesting that something unseen had crossed its path and rewritten part of the galaxy's hidden history. The scar in the stream. The turning point arrived when astronomers began examining data from the European Space Agency's Gaia mission, a project designed to map the precise positions and motions of more than 1 billion stars. With that unprecedented level of detail, GD1 no longer looked like a smooth stellar ribbon. Instead, researchers noticed a strange absence, a narrow gap where stars seemed to have been pulled away, followed by an unexpected spur of stars drifting off the main path. The structure looked less like a natural variation and more like the aftermath of a collision, as if something had punched through the stream and scattered its members outward. At first, scientists considered whether the disturbance might be an illusion created by observational limits or statistical noise, because stellar streams are faint and difficult to trace across the sky. But repeated analyses confirmed that the features were real and their geometry carried a consistent signature of gravitational interaction. The gap was too sharp to form gradually, and the displaced stars followed trajectories suggesting a sudden, energetic encounter rather than slow galactic evolution. In effect, GD1 appeared to contain a scar, frozen in motion, recording a moment when its quiet orbit had been violently interrupted. As researchers compared the data with computer models, the mystery deepened. The stream's distortion implied that a massive object had passed through relatively recently in cosmic terms, perhaps within the last billion years, yet no visible satellite galaxy, star cluster, or known structure occupied the region where the encounter must have occurred. Gravity had clearly done the damage, but the source of that gravity seemed to be missing. This contradiction transformed GD1 from a simple astronomical curiosity into a forensic investigation, forcing scientists to ask whether the galaxy was hiding something invisible that conventional observations could not detect. Hunting the invisible intruder. To understand what had happened, astronomers turned to a technique that feels almost like rewinding time. Using orbital simulations, they reconstructed the motion of GD1, running the stream's trajectory backward through millions of years to estimate where and how an encounter might have occurred. These models allowed researchers to test different scenarios, adjusting the mass, speed, and direction of hypothetical objects until the simulated stream reproduced the same gap and spur seen in real data. What emerged was not a random distortion, but a precise gravitational fingerprint, suggesting a fast-moving intruder that crossed the stream at a specific angle and velocity. The first suspects were familiar ones. Could a known globular cluster have passed nearby, or perhaps a faint dwarf galaxy hidden in the Milky Way's halo? Astronomers compared catalogs of known objects against the reconstructed path, but nothing matched the required timing or mass. Even massive molecular clouds were ruled out, since GD1 lies far from the dense galactic regions where such structures exist. Each eliminated possibility sharpened the mystery because the disturbance demanded an object heavy enough to reshape thousands of stars, yet invisible enough to leave no trace in telescopes. Researchers then explored more exotic explanations, including the possibility of an intermediate mass black hole drifting through the halo. While black holes are invisible by nature, they usually reveal themselves through surrounding radiation or gravitational effects on nearby matter, and no supporting evidence appeared in the region. The models kept pointing towards something stranger, an object composed mostly of dark matter, a type of matter that does not emit light but exerts gravity. If true, GD1 had not merely been disturbed by chance. It had become a rare detector, capturing the passage of an unseen structure that might belong to the hidden architecture of the galaxy itself. The mind-blowing constraint. As the simulations grew more precise, the mystery shifted from what struck GD1 to what kind of object could possibly leave such a clean and violent signature. Researchers found that matching the stream's gap and spur required a surprisingly narrow set of conditions. The intruder had to carry a mass roughly between a few 100,000 and 100 million times that of the Sun. Yet it also had to be extraordinarily compact, squeezed into a region no more than a few dozen parsecs across. In other words, whatever crossed GD1 was not just heavy, it was dense, concentrated, and moving fast enough to slice through the stream without completely destroying it. This result shocked many astrophysicists because standard models of cold dark matter predict that most dark matter subhalos should be diffuse and extended, more like clouds than bullets. The object implied by GD1, however, behaved more like a gravitational projectile, compact enough to create a sharp wound, rather than a gradual distortion. Statistical analyses suggested the required density sits several standard deviations above what conventional simulations expect, placing the event near the edge of theoretical comfort. Instead of confirming existing models, the data seemed to push against them, forcing researchers to question whether something about dark matter's small-scale structure is missing from current understanding. Importantly, this was not a speculative idea built on imagination alone. The constraints came directly from orbital dynamics, from the measurable positions and velocities of stars that still carry the imprint of the encounter. The stream itself acts like evidence preserved at a cosmic crime scene, where the shape of the disturbance reveals the properties of the invisible intruder. For the first time, astronomers realized that stellar streams like GD1 might not simply map the galaxy's past, but could also expose the hidden physics of dark matter, transforming a single scar in space into a test of fundamental cosmology. What this means for dark matter. For decades, dark matter has been one of the central pillars of modern cosmology, proposed to explain why galaxies rotate faster than visible matter alone can account for. According to the dominant cold dark matter model, the Milky Way should be surrounded by countless small subhalos, invisible clumps whose gravity quietly shapes the motion of stars. Yet most of these structures have remained frustratingly difficult to detect, leaving astronomers to rely on simulations that predict how they should behave. The GD1 disturbance changes that dynamic because it offers something rare in astrophysics, an indirect but measurable interaction between dark matter and ordinary stars. If the compact object inferred from GD1 truly represents a dark matter subhalo, then it suggests that at least some of these structures are denser and more concentrated than expected. This possibility opens the door to several competing interpretations. One idea proposes that dark matter particles may interact with one another in subtle ways, allowing subhalos to collapse into tighter configurations. Another suggests that the Milky Way's history of mergers and tidal interactions may compress certain regions of dark matter beyond what simplified models predict. A more cautious interpretation argues that an unseen astrophysical object, perhaps an unusually quiet black hole or a faint remnant galaxy, could still explain the data, although current evidence does not strongly support these alternatives. What makes the debate so compelling is that the stakes reach far beyond a single stellar stream. Dark matter shapes the formation of galaxies, influences cosmic structure on the largest scales, and determines how matter clumps together across billions of years. If GD1 is revealing a flaw in our assumptions, then it means astronomers may need to revise part of the framework used to describe the universe itself. The mystery therefore shifts from a localized anomaly to a broader question about whether the invisible scaffolding of the cosmos is more complex and more dynamic than anyone expected. A galaxy full of invisible collisions. Once astronomers realized what GD1 might be revealing, they began to look at the Milky Way differently. The galaxy is threaded with many other stellar streams, each one the remnant of a long-forgotten cluster or dwarf galaxy, stretching across the halo like faint scars of ancient encounters. If one stream carries evidence of an invisible collision, then others may hold similar clues waiting to be uncovered. Modern sky surveys, combined with the precision of Gaia and future observatories, are turning the galaxy into a vast laboratory where gravity can be studied through the motion of stars rather than through light alone. This shift has changed the role of astronomers from observers into cosmic detectives. Instead of searching directly for dark matter, they analyze distortions, gaps, and subtle asymmetries, reading them the way geologists read layers of rock, or forensic scientists examine impact patterns. Every irregularity becomes a question. Was this shaped by known physics, or by something hidden passing silently through the galaxy? The work is slow and meticulous, requiring years of data and careful modeling, yet each new stream mapped in detail increases the chances of finding another gravitational fingerprint. What emerges from this effort is a humbling perspective. The Milky Way is not a stable structure drifting peacefully through space, but a dynamic environment where unseen forces constantly interact with visible matter. The stars we observe are only part of the story, tracing paths influenced by structures we cannot directly see. As more streams are discovered and analyzed, the hope is that these fragile ribbons of light will gradually reveal the invisible architecture surrounding us, turning quiet stellar motion into a map of the galaxy's hidden collisions. Somewhere in the dark between the stars, something invisible crossed a silent river and left a wound that still moves through the galaxy today. As we trace these hidden collisions, we begin to see the universe differently. So follow the journey, because the next discovery may already be passing us by.